Good day, grade 12s. Today I want us to tackle graphs on vertical projectile motion. And so I know that usually you start by seeing my face, but today we're going to do it a bit differently. I just want to get right into it. Please don't forget to subscribe. Just hit that subscribe button so that you can see the lessons that I post in future. And also don't forget to also post a comment if there's something that you'd like for me to explain better. Otherwise, you can hit me up on my email. That's mlungisi.m.ngosi@gmail.com if there are any questions or any queries that you would like for me to handle. All right, let's get into it. So I want us to talk a little bit today about graphs on vertical projectile motion. Today will be kind of a DIY type of session, so I'll be handling a lot of things on my own. So if the images just become a little bit unsavory, please just forgive me a little bit. I'm trying to do everything on my own. All right, let's get into it. Right, so when we talk about vertical projectile motion, in our previous video we had talked about vertical projectile motion as motion under the influence of gravitational force. But today I want us to look at graphs that have to do with vertical projectile motion. Now, first of all, I want us to just go back a little bit. In math, you've got graphs, different types of graphs, straight line graphs. You've got parabolas, hyperbola, and so on and so forth. So when it comes to vertical projectile motion, we're going to have graphs that have to do with velocity time, acceleration time, and as well as position time graphs. We're going to look at examples, different examples on each of those graphs. And so let's get to it. So first of all, when it comes to graphs, whenever you've got A directly proportional to B, for instance, okay? Let me just adjust my image there a little bit, okay? If I've got A that is directly proportional to B, right? So whenever A is directly proportional to B, we're then simply saying that whenever you increase B, it means that A will also increase, okay? Notice how we read it. We'll read it from, we call this the independent variable, and this is the dependent variable, okay? So it means that A depends on B. Whenever you change B, A also changes, okay? So when A is directly proportional to B, okay, we know that whenever you increase B, therefore A will also increase. Now, however, then when it comes to graphs, what we need to do is now move a step further and say, okay, but in order for us to now introduce an equal sign, okay, now what we need to have is that we need to introduce a constant, okay, multiplied by B. What that simply means is that if I say A is directly proportional to B, what it doesn't do is that it doesn't tell me by how much A actually increases with every single increase in B. So if I put an equal sign, now I am simply saying with every single increase in B, A will increase K times. Let me make an example. In maths, you would have something like y is equals to 2x, okay? Just a simple example like that. Whenever I increase x by 1, y increase what? 2 times, okay? So in essence, that is how we look at graphs. So now, let's go into vertical projectile motion. You've got a graph, or rather you've got an equation, Vf is equals to Vi plus G delta T, okay? Right. So now let me just make an example. Just make a, yeah, just an example that I'd want for us to take. Let's say, for instance, we're taking a situation where we assume, okay, let's make an assumption that our initial velocity is 0. There's something that I want to see there. So if our initial velocity is 0, right? So what does that do? What am I left with? I'm left with Vf is equals to G delta T. Okay, now have a look at this. So when I said A is equals to K times B, what it simply meant is that in order for this to be considered as a direct proportion, all right, it simply means that next to my independent variable, there must be a constant. So K is actually a constant, okay? So K is a constant. It means that it's a number that is not supposed to change. Otherwise, if it changes, then in this case, I cannot claim that A is directly proportional to B. I know that sounds a little bit tedious, okay? But nonetheless, it is something that you ought to understand when you're going to deal with graphs, okay? Right, now look at this. Now all of a sudden I've got Vf is equal to, can you see I've got an equation now, equal sign, now G delta T. Now if I look at Vf and delta T, right, how do I relate with them? Okay, or how do I relate them together? Look at this G. Is G a constant? Well, remember when it came to vertical projectile motion, we said gravitational acceleration is always a constant value, and that value is 9.8 meters per second squared. We always deal with constant acceleration in physics. So as a result, we know that our G value is a constant 9.8 meters per second squared. Now, whether it is positive or negative depends on your choice of direction. Whether you chose up as positive, if you took up as positive, so that value will be negative. If you took down as positive, obviously that will be a positive 9.8 because gravitational acceleration always acts vertically downwards. Okay, so as a result, one thing that I want you to notice now, because that is a constant, it simply now means that Vf is directly proportional to what? To T. Now, something that I forgot to just mention there. If I say A is directly proportional to B and they ask me to draw a graph of A against B, okay? So I'm supposed to draw a graph of A against B. It will always be a straight line graph, okay? Right, if I have two things that are proportional to each other and I draw a graph of A against B, then it means that it will always be a straight line. Now, look at this. I've got Vf, right, and T. There's a constant there. So it means that if I draw a graph of velocity, okay, against time, all right, so, well, guess what? Velocity is directly proportional to time because there's a constant next to the variable, independent variable. So guess what? It will be a straight line graph. Now, of course, the shape of the graph will depend on the value of G, whether positive or negative. Okay, remember in mathematics, okay, you use that. Some call it the right hand tick. Okay, right. So if your gradient is positive, then you know you're going to have a shape that looks like that. If your gradient is negative, okay, so they call it the right hand tick, that if it's positive, okay, you know how you tick, you always tick that way, right? No one, if it's negative, I mean, you hardly find people who tick going that way. So in this case, this is a negative gradient and that's a positive gradient. So That all depends on your choice of direction. Okay, right. Now just another thing that I want you to notice. So it means that when we draw a graph of velocity against time, it will always be a straight line graph. Why is that? Because velocity and time are directly proportional to each other. Now think about it. In maths, you can have y is equal to m times x. Okay, you call that value what? The gradient, isn't it? So m represents what? The gradient. So you say mx plus c, right? Now notice, if my initial velocity was not 0, it simply means it would just simply shift my graph. My graph is not going to start at the origin, but it will start somewhere along the vertical axis, right? So in this case, all that we're simply saying is that y is equals to mx plus c. M is our gradient. Look at this. Now you've got what? Vf. Okay, if we put that next to each other, delta t plus vi. So I've written the same equation just in another way. So it means your gradient there, m, is now g, which is 9.8. Okay, right, let me just move this a little bit. Okay, so your gradient there is 9.8. Okay, and then your vi is actually your c value, which is just simply going to shift your graph. Okay, right. So that's about the graph on the straight line graph, or velocity against time. Now here's another thing. If I wanted to talk about displacement against time, or position against time, I want you to notice we've got an equation. Okay, we've got an equation, delta x is equals to vi delta t plus 1 over 2 g delta t squared. Okay, right. So if you look at this equation, again, I'm going to make that assumption. If I take initial velocity as 0, right? So what am I left with? I'm left with delta x is 1 over 2. Okay, that whole thing disappears because anything multiplied by 0 becomes 0. So now you've got half g delta t squared. Okay, now notice what are we left with? We're left with that whole thing. Now notice, if you say a half is a constant, right? It means that a half will remain a half forever and ever, right? G is also a constant. Now what do we find ourselves with? We find delta x now equal to a constant. So that whole thing is a constant. Half of g is our constant multiplied by delta t squared. So therefore it means that delta x is now directly proportional to what? To t squared. Now if you think about the type of graph that you would have in maths, when you've got y is equals to ax squared plus bx plus c, right? So what type of a shape is that? It's a parabola. You're quite right. Okay, right. It would be this kind of a graph. Now, as to whether it is a smiling face, okay, a smiling parabola, or in this case a sad parabola, it all depends on this value of a. So this one, your a value would be greater than 0. Okay, that's a smiling graph. Here a would be less than 0, meaning the coefficient of the square x squared term, okay, determines the shape of your graph, isn't it? Now let's go back to the one that you had there. So if your g value, if you took downwards as positive, okay, then it means that this whole thing becomes positive, and as a result, the shape of your graph, look at this, you've got delta x directly proportional to the square of t. So if I asked you to draw delta x against time, right, it means we would actually get the shape of a parabola. But now what would determine the shape of a parabola would actually be that value of g there, the coefficient, isn't it? Okay, I'm trying to rush through this so that we actually get to the meat of this section. Okay, so all I'm simply saying to you is that if I draw delta x against t, right? So I'm expecting a parabola. Most of the time, we would actually take upwards as positive. I'll show you why that would be the case. When you have to draw the position time graph, it makes it quite easy for you to interpret when you do that. So if we take upwards as positive, it means that the value of g becomes negative 9.8. So as a result, we're expecting that our parabola would actually be a said parabola. It would be a shape that looks more or less like that. So just remember this. So here we took A directly proportional to B, we got a straight line. So we said if we draw a graph of a straight line graph, we know that VF is directly proportional to T, right? So now we get a straight line, and we said what will determine that shape is the value of G, isn't it? Whether it is a positive or a negative, that will determine the shape. Don't worry, we'll tackle some questions for you to understand that better. I hope that makes sense. So I think without any further waste of time, what I want us to do is to tackle some graph related questions. All right, just to show you in past examinations how they had actually asked these and how they tackled them. I hope that you're ready. Okay, right, let's get into it. All right, so I sourced this question from the SCE exam, the March-April 2020 question paper that was supposed to be written. I found it to be quite an interesting question. All right, and I'm gonna go through it with you. I hope you can see it clearly. All right, now it says a ball is thrown vertically downwards from the top of a building and bounces a few times as it hits the ground. Okay, they say the velocity time graph below describes the motion of the ball from the time it is thrown up to a certain time t. Note, take downwards as the positive direction and the ground as zero reference. Okay, the graph is not drawn to scale. The effects of air friction are ignored. All right, now let's get into it. Okay, so what I want us to do first, before we even get to answering the questions, I want us to kind of analyze what is happening in this picture. Okay, I want us to simply look at it, what exactly is going on in the picture, and as a result try to find to draw sort of a space-time representation of this picture. Okay, so they told us, okay, they are going to throw, okay, that's what the examiner says, throw, a ball is thrown vertically downwards. All right, so now I want you to think about it. They threw the ball downwards. All right, so meaning its initial velocity is not zero, right? So at the beginning of your graph, what is your velocity value? Can you see it's that positive 10 there, né? All right, so that simply means that, by the way, it's a positive value and they threw it downwards. So it simply means that we are taking downwards as positive, as the examiner stated there. So in this case, we threw the ball. Okay, let's draw our building there. Okay, so here's our ball. It starts at a velocity of 10 meters per second. Okay, and then what happens as it goes down? The velocity increases. Can you see? As it goes down and down and down, the velocity increases. So this is the velocity when it reached the ground. Now ladies and gents, what I want you to please note, okay, whenever we do questions on projectile motion, all right, we take that final velocity or the velocity when something lands on the ground. Remember that we don't consider it when it actually hits the ground, because at that point it is no longer considered to be in free fall. Okay, why? Because gravity would not be the only force that acts on it. So as a result, it's only in free fall, okay, whilst it's still falling, just up until just the moments just before it lands on the ground. So here's our ball. Starts at 10 meters per second, okay, goes down. Here it is, the velocity is increasing, okay, so ball goes down, velocity increases, and then moments before it hits the ground, it lands on the ground, okay, so that velocity would be 29.6. So this velocity here would be 29.6. Oops, sorry. So that velocity would be 29.6. Okay, right. And how long did it take to get there? It took about 2 seconds. Can you see that now? Right. Now, remember, then it lands on the ground. So it's this abrupt motion here. So this is moments before it landed on the ground, and then quickly, boom, right? It changes direction. It's this moment here. It hits the ground quickly and then immediately changes direction. It's now going upwards. So if we took downwards as positive, obviously it means that upwards would be negative, and that's why it changes there. All of a sudden that velocity becomes goes on the negative side of your graph, okay, and then what happens as it goes up, right? Remember what's happening to the velocity. It's decreasing now, okay, until it gets to maximum height. So if you think about it, here it is when it left the ground. So the velocity with which it left the ground was velocity x. We don't know what that speed is there, okay. We know it should be negative, okay. And then what happened? Then it started to go upwards, all right. Remember, the velocity is negative, it's going up, but when it gets here, the velocity is 0. So the velocity was decreasing, up, it's negative all the way here until we get to this point here, and we know when the your graph cuts across the time axis there, this is where we get to maximum height. So we know this is our maximum height, okay. So this is this point here. All right, I think it will be best if we label it. I'm going to label it for you as we continue to do the question. Right, so what happens there? There's our maximum height when it gets there after 4.99955 seconds. All right, and then what happens? Then the velocity starts climbing up again, and on the positive side. Why? Because now again it's going down. Can you see? So the velocity is increasing in the positive direction. So I want you to imagine positive, 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 positive. Can you see? Positive, positive, positive. And then all of a sudden it changes. It's this point here. All of a sudden it changes and it becomes negative, 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 negative all the way, right? Reaches maximum height. The velocity is 0 here, and then again starts becoming positive because it's going down again, right? So the velocity is positive yet again. So in this case, so it's this point here on your graph. It's increasing, right? And then what happens? It hits the ground. It's this point again, right? So the velocity with which it landed on the ground is 27. So the velocity there is 27, okay. And then it changes velocity quickly. It changes direction quickly, right, between this point and that, and goes up yet again. And it seems our graph only got up until maximum height just after the second bounce, right? So I want us to start tackling this question together. So I want you to look at this graph. Here's our ball. leaving 10 meters per second, right? And then it gets to 29.6 meters per second at that point there. Okay, so it's that point over there. All right, this is when it got to the ground, 29.6. It left the ground with a velocity of x, so it's that velocity there when it's leaving. Okay, and then went up and then reached maximum height at this point here, 4.99955 seconds. Okay, and then started going down yet again and landed on the ground at 27 meters per second. Now, I want you to just think about it. This is, I think in the previous video, I told you about a time symmetry. We said when an object leaves a certain point and comes back to the same point, do you see? We said the velocity with which it leaves, or rather the speed with which it leaves, will be the same as the speed with which it lands back, provided that that is the same position again, right? So this kind of tells us what would be the value of x there. It means x would be 27. So it would be negative 27, and it comes back with the same speed, 27 meters per second, because this position and that position are exactly the same. Okay, right. And this now when it gets to that maximum height there, another maximum height, right? And it lands at that maximum height there at a time t. So we know that the time is t there. So we'll deal with that as we go on. Right. I hope that kind of makes sense. So I want us to tackle that question. So I just want you to notice. Do you notice there's a time delay between when it actually hits the ground and that point? Just it spends a little bit of time on the ground here. This is when it was bouncing, and then it leaves the ground. So there's a bit of a time delay between the arriving on the ground and the leaving the ground. That time delay is about it landed on the ground in after 2 seconds. It left the ground after 2.2 seconds from the beginning. So what time did it spend there on the ground? It must be 0.2, right? Okay, so let's interpret, let's answer the questions that the examiner gave to us. All right, I hope you can see those questions as we are going to tackle them together one by one. Ultimately, I want you to benefit to the maximum when it comes to this. So here's our ball, went down, okay, bounced, okay, maximum height, another bounce again, and then another maximum height. So maximum height 1, maximum height number 2. Right. Now let's answer the questions. They say, oh, by the way, let's remember something that I want you to always remember. Please remember this. Okay? So, if you remember what I had said to you about the gradient under a velocity time graph. Okay? So, the gradient under a velocity time graph will always be the gravitational acceleration. You remember our VF is equals to G delta T equation. Okay, if you want to, we can say plus VI. So VI is that, you remember I said to you, if VI is not 0, what it simply does is that it shifts your graph. Do you remember that? So our VI value is 10, and that's why the graph did not start at the origin. If we started with an initial velocity of 0, our graph would have started there at 0, right? But now because your initial velocity was 10, and that's why your graph started at 10 meters per second. However, what I wanted to just simply point out to you, if we take this as a maths graph, y is equals to mx plus c, right? Remember, in our time axis, our x-axis, we've got time, right? X is time. Now you notice there, m is what? The gradient, the gravitational acceleration, isn't it? So the gradient underneath a velocity time graph is gravitational acceleration. Now I want you to note, this is a positive gradient, isn't it? So it means that our g value is a positive 9.8 meters per second squared, right? So please note, whenever the examiner asks you about the gradient under a velocity time graph for projectile motion or for free fall, we know that that gradient there represents gravitational acceleration. I hope that is clear to you. Right, now let's get to the question. Now they say write down the speed with which the ball is thrown downwards. Okay, we've already established that, right? Okay, with what speed did they throw it down? Right, you got it right. It's 10 meters per second. So the initial velocity there, the velocity with which they threw it, is 10 meters per second. So we know that the speed of the ball right at the beginning, and by the way, they said speed, so we're not obliged to show direction. So that would be 10 meters per second. Great. Okay. They say all parts of the graph have the same gradient. You see, they're getting to that part now. Okay. We said, what does gradient represent? Gravitational acceleration, right? So they say all parts of the graph have the same gradient. Give a reason for this. All right. So why is that the case? Because the gradient represents what? Gravitational acceleration. So in this case, in tackling, this was 3.1. So 3.2, because gradient, okay, gradient represents gravitational acceleration, which is a constant 9.8, isn't it? Which is constant 9.8 meters per second squared. Super. All right. So remember that the gradient underneath the graph is a constant value, which is that 9.8. So let's go to 3.3. Now they say calculate the height from which the ball is thrown. Now, ladies and gents, please, I want you to stay with me on this one, okay? Because there are two ways that I want to actually show you on how I'm going to tackle this question. And I'm going to show you something else about the velocity time graph besides the gradient, okay? So they want the height from which the ball was thrown. Now, I want you to notice, we're going to a space-time graph, right? Would you agree with me that if I consider the moment from which the ball was thrown to the moment with which the ball landed on the ground, if I took the displacement of the ball between those 2 points, if you don't mind, I want to just label the points there. Maybe let me use a different color. Okay, so let's call that point A. Let's call that point B when it landed on the ground. Let's call that point C when it bounced off. Let's call that point D when it left the ground. Okay, let's say we've got point E when it actually landed again on the ground. Okay, when it bounced, let's call that point F, and then let's call that point G. Okay, that occurred at time T. So now, if I took information between A and B, all right, when it left, when it was thrown down, and then until it landed, do you agree with me that that will give me the displacement? Okay, so I can simply say, okay, I've got initial velocity, I've got final velocity. How long did it take to land on the ground? It took 2 seconds. Can you see that? Right, so I can say, well, I've got initial velocity, I've got final velocity, I've got time, right? And I also know gravitational acceleration, right? So you can choose which equation of motion. You can say delta x is equals to delta t plus 1 over 2 times a delta t squared. Okay, right, so what is my initial velocity? It's 10, right? The time that it took was 2 seconds. Okay, plus 1 over 2 times a. Remember, we said our gradient is positive, so it means it's a positive 9.8, okay, multiplied by 2 squared. Okay, right. And we're simply going to take our calculator there. Okay, we're looking for that delta x value. Okay, let me quickly just grab my calculator there. Right, so we're going to say this is 10 times 2 plus 0.5 times 9.8 times 2 squared. Okay, so I get 39.6. So I get a value of 39.6 meters, right? You could have chosen a different equation to use. Okay, perhaps if you wanted to, you could have used delta x is equals to vi plus vf, okay, over 2 times delta t. Sorry about that, writing right at the edge. Okay, you would have actually gotten to the very same answer as well. So that would be 10 plus vf, so that would be 10 plus 29.6, okay, all over 2, okay, multiplied by the 2 seconds for time. Okay, so that would be 10 plus 29.6, that would be 39.6. Oh, but by the way, you can just simply cancel these two to divide by 2, so that's 10 plus 29.6, that would give you 39.6 still. Okay, so the height of the building is 39.6. Now here's what I want to do. I said I wanted to show you how to tackle this a little bit differently. Okay, now one thing I also want you to know is that the area underneath a velocity time graph, so the area underneath the graph, the velocity time graph, actually represents displacement. Okay, so and how we can prove that is that if you take area is, you always say, in a sense, length times breadth, isn't it? Length times breadth. If it's a triangle, obviously you've got a scaling factor of 1 over 2, okay, but it's 1 over 2 length times breadth, or you call it base times height. It's the same thing, right? Oops, sorry for that disruption. Electricity just went off in our area. Sorry for that little disruption. Now, we're still saying if we took the area underneath the graph, okay, that simply means that area underneath the graph would give us the displacement. I want to show you that mathematically, right? If you say length times breadth, so if you say length times breadth here, the length actually represents time, right? So that would be time, okay, multiplied by the, okay, so whichever one you okay, so the breadth in this case would be your velocity, right? But if you want to see it well, so velocity, that's in meters per second, okay, multiplied by time, which is in seconds, right? Now, if you know anything about exponents, you'll see there a second per second and second, both of these have the same basis, right? And what do we do when we multiply two exponents, or rather when we multiply two bases, right? We normally add the exponents. So this will be minus 1 plus 1, which will give us 0, anything to the power 0 gives us 1, right? So you'd have meters second minus 1 plus 1, okay? So that will give us what? Meters second to the power 0. Anything to the power 0 is 1, so therefore that will give us meters. So what I'm simply trying to show you is that when we take the area underneath the graph, it actually gives us that displacement. So how I can actually answer the very same question, look at what I'm going to do now. I'm going to simply say, okay, now look, what shape do I have underneath my graph? Let me just try to show you there. All right, what shape do I have underneath this graph here? Okay, from the moment, remember it's between A and B, it's between this point here and that point there when it landed on the ground, this point and that point. What shape do I have under this graph? So now it's a trapezium, but not too many people are familiar with the formula for calculating the shape of the area of a trapezium. So what I'm going to do is I'm going to break it down into two parts. Okay, do you see? I'm going to shade this. Okay, so you've got that rectangle there, and then you've got another part. I'm going to shade it in a different color, which is a triangle there. Okay, right, so you've got those two areas there, right? So how I can tackle it, if the examiner was strict enough to say using the graph, I would actually have only this option in order to tackle this question. So now I'm simply going to say, okay, right, so to calculate the same thing, all right, I'm doing the same thing, I'm just showing you a different method, right? To do the very same thing, I'm going to say the area underneath the graph. Remember, I've got that triangle, so it's going to be half base times height plus, okay, that rectangle there, that's length times breadth. Sorry for that mix up. So this is going to be half. So what is the base of my triangle? It's between this point here and that point there, right? So our base is 2, right? So it's between 0 and 2, so our base is 2 times our height. Now please be very careful here, right? The height of my triangle, remember a triangle doesn't start at 0, it starts at 10 and ends at 29.6. So what would be this height? It would be the difference between those 2 points, right? So it would be the difference between those 2 points. So 29.6 minus 10, that would give me 19.6. Sorry, I wrote 1.9 there. So that would be 19.6. Okay, sorry about that little mess there. Plus, let's go to our rectangle now. It's going to be length, which is 2, times my height there, and my breadth, which is 10. Okay, and notice what's going to happen, half, so that cancels with that, I'm left with 19.6. okay, plus 2 times 10, that will give me 20, and then 20 plus 19.6, well, guess what, we've got that very same answer, which is 39.6 meters. Okay, just remember that when you've given a velocity time graph, the area underneath the velocity time graph will always give you the displacement. Okay, right, great stuff. I hope that you can see that very well. If you don't mind, I need a little bit of space, so what I'll do is I'll just move this stuff over so that I can tackle the other questions. I'll tackle them onto this side so that we don't lose what we're doing there. Right, so the next question says calculate time t shown on the graph. So what are they looking for? They're looking for that time there, time t. Okay. Now there are several ways in which we can do that. Okay. So you know what? Remember we said we know what the gradient of this graph is, isn't it? Okay. Do you mind if we use gradient? Okay, let's do that. Let's do that. So now what I'm simply going to do is I'm going to say for 3.2, okay, so I'm going to write it over here. Right, I want to find out what is the value of t. So I'm going to say, all right, let's take mathematically. We usually say gradient. How do we tackle gradient? We say m is equals to the change in y over change in x. You remember that in maths, right? So m is equals to change in y over change in x. But remember, in this particular case, we don't have y and x, but it's what? Change in v over change in time. Okay? Change in velocity divided by change in time. So I'm going to work it out through that gradient there, right? But what's the value of my gradient? You remember, right? We said gradient represents what? Gravitational acceleration. So I know that m is already 9.8, right? Which is equals to, now I'm going to take those 2 points there. If you don't mind, I'm just going to label the points there. This is the position. X is 8, right? And y is minus 25. Okay, right? And what about that value here? X is t, right? And our y value is 0. Okay, so now continuing with our question. So we know that we're going to say, all right, so that's change in v. Remember, this is the x and the y. So this is the time and this is the velocity value. So let's label, I don't know which one you want to take as, okay, let's take this one as t1. So if this is t1, this will be v1. Then let's call this t2. Okay, so that will be v2. So normally when we calculate the gradient, you say v2 minus v1, okay, and y2 minus y1 over x2, oh sorry, our x value is t, so t2 minus t1. Remember that in the way that you order the values there, you're going to do the same here in terms of, you know, on the axis. Now v2, we said that's 0, okay, minus v1, and v1, remember there's a minus sign there, minus a minus 25, okay, divided by t2 is t minus, okay, 8. I hope you all can see that, right? So now what we're simply going to say is, all right, so now we've got, and all of this is equals to what? 9.8. All right, so we're going to do a little bit of gymnastics mathematically. Okay, so we're going to say 9.8. Okay, so if we cross multiply, right? So this is, we're just going to say divide by 1 so that we know that 9.8 divided by 1, we haven't changed anything, right? So we cross multiply and we're going to say t times t minus 8 times 9.8. So this is 9.8 into t minus 8, right? Which is equals to 1 multiplied 0 minus a minus 25. Negative times a negative will be a positive. So this is 0 plus 25, right? So this is 25 times 1, and this should give us 25. Now all we can simply do, divide both sides by 9.8. Okay, divide by 9.8 so that we can cancel that out, right? 25. Okay, let's take our calculator again. So this is 25 divided by 9.8. I seem to get the value 2.55. Okay, I'm just gonna round that off. So t minus 8 is 2.55. Okay, right? So t is equals to, if I take that to the other side, obviously it becomes positive, so therefore this is 10.55 seconds. So it means this value here is 10.55. Now someone else could have chosen to do this differently, and I want you to be very careful if you're going to follow this approach, right? Someone else could have said, oh, but why didn't we use equations of motion? There was really nothing stopping you from doing that. You could have done that quite easily. Let me show you. So you could have said, all right, let me take initial velocity there. So that's minus 25. Final velocity is 0, right? But I also know what is my gravitational acceleration, isn't it? So you could have said, all right, let me use the first equation. I'm answering the very same question. So Vf is equals to Vi plus G delta T. Okay, so you could have used that there. So Vf in that case, remember your final velocity was 0, right? Initial velocity was minus 25. Okay, plus 9.8, sorry, I'll just try to cover that. Okay, 9.8 delta t. Okay, delta t. So then what happens? Okay, take that to the other side, it becomes 25 is equal to 9.8 delta t. Now notice we're going to divide both sides by 9.8. Okay, that cancels that. So your delta t would be 25 divided by 9.8. If you remember, it's that value that we got. 25 divided by 9.8, we got 2.55. So that's 2.55 seconds. Now, many people would actually just leave that answer there. But remember, we want the value of t in relation to this graph here. We don't want to know this time here, 2.55, would be the time that it took the ball to move from this point here where it left the ground. If you remember our picture, when it left the ground at F, okay, and it reached maximum height at G, right? So that's not what we're looking for. We're looking how long did it take from the moment it was thrown up until this point here. So in this case, from that point there, so if you said this is 2.55, it wouldn't make sense because that time there is 8 seconds, unless you can move back in time, which I hope we could, but that is not possible. Okay, so I hope that kind of makes sense, right? Now, what I want us to do, let's move on to the next question. So what you would do for that question, sorry, so it means that you take that time there and you add the length of time that it spent during this here, during this motion here. So it's 8 plus 2.55, and so that's how you'd land to that t is equals to 8 plus 2.55, and you'd still get the same answer, which is 10.55 seconds. Okay, I hope you can see how it helps to know that the gradient under velocity time graph is actually the acceleration, gravitational acceleration, and that the area gives you the displacement. Okay, right, now let's go to the next question quickly. All right, now they say write down. You see, when they say to you, you must write down, it means that it's something that is not really meant to be calculated. They said, write down the time that the ball is in contact with the ground for the first bounce. Now, I want you to notice, where is our first bounce? It's here. How long did it take? It's between 2 seconds it landed on the ground, 2.2 seconds later from the point of throw, it's now leaving the ground. So how long did it spend here? You're quite right. It's going to be 2.2 minus this 2, so it's going to be 0.2 seconds. So in answering that question, we know that it would have taken, so the time would be 0.2 seconds. Okay, so that's 3.4.1. Okay. Alrighty. Okay, sorry, I just need to adjust that a little bit. Alright. Okay, so that would be 0.2 seconds. Remember that time is always measured in seconds, right? And then they say write down the time at which the ball reaches its maximum height after the first bounce. Okay, reaches the maximum height after the first bounce. You see how much it helped for us to draw that graph now. So if we look at that, so after the first bounce it reaches the maximum height there, and I even showed you on that graph there. So it reached the maximum height after 4.955 seconds. So in answering that question, 3.4.2, so we know that it took 3.455 seconds. Okay, right. So we want the value of x. Okay, the value of x. Do you notice how they constantly say write it down? So it means that you are not meant to calculate it. So you remember what I had said to you, right? We left the ground here, we landed back on the ground there, and so this is a time symmetry situation. So we landed back on the same point, at the same point, at 27 meters per second, and we left there at, it should be at minus 27. Can you see it's even below that 25 mark? So in this case we should know that x is minus 27 meters per second. So x is minus 27 meters per second. Okay, so that is how we would tackle it. Okay, and then the last question, they ask us, is the collision of the ball with the ground elastic or inelastic? All right, give a reason for the answer using information on the ground. Now, how would we know whether it was elastic or not? It means that kinetic energy would be conserved, isn't it? Now look at this. When we say something is conserved, we mean that kinetic energy is conserved. It means kinetic energy before and after the collision would actually be the same, right? Obviously the mass of the ball doesn't change, we assume, right? So if you look at this, the velocity with which it landed on the ground was 29.6, but it leaves the ground at minus 27, at 27 meters per second, right? Okay, so what does that mean? It means that it has lost some of its kinetic energy. And obviously, you would imagine if a ball lands on the ground, you'd hear a sound, isn't it? So some of the energy would be used to produce that sound, right? So the universal law of energy simply says energy cannot be created or destroyed, but it's transformed from one form to another. So in this case, some of that energy would be used to produce the sound, or even if you think about the ball distorting a little bit, some of that energy would be used in the distortion or the deformation of the ball for that moment. Okay, so so the answer is that it is an inelastic collision. And why is that? Because kinetic energy before collision is not equal to kinetic energy after, or you can simply say that kinetic energy is not conserved. Okay, right, great stuff. I hope that that made sense in terms of our velocity time graph. I know that it's been quite a challenging question. All right, so I want us to now tackle another question on graphs, but I want us now to kind of tackle a position time graph. Okay. All right, so we've got another question here. All right, I took this from the September 2019 paper. It was the Gauteng preparatory exam. Okay, so it was a prelim. So let's tackle that in terms of the position time graph. Now, they say the sketch graph below shows the motion of a ball that is thrown vertically upwards from the balcony of a building. Right, they say the ball takes 0.6 seconds, okay, to reach its highest point. Okay, after which it falls downwards downwards past the balcony to the ground. Ignore the effects of air friction. Okay, now let's try and analyze that graph. Okay, we're going to look at the questions just now. Okay, let's analyze that graph. It is a position time graph. So first of all, remember, we said a position time graph, all that it simply shows us, okay, is we did agree that displacement time is a parabola, isn't it? You remember? So can you see the shape of that parabola? Can you see that it is a said parabola? Okay, kind of a said graph. And if you remember what we had said, right? We said, all right, we know that if we take, for instance, from our equations of motion, okay, then we know that this thing doesn't write properly. Okay, so then we know that if we take delta x is equals to vi, okay, delta t, okay, plus 1 over 2 a delta t squared. All right, this is our equation. So what this simply indicates to us, okay, we know it's going to be a parabola, but now the coefficient of x squared, all right, is what determines the shape of the graph. We said when the coefficient is positive, then it should be a smiling graph. But if the coefficient is negative, then it should be a sad graph. Okay, so now look at the graph. The result is that we get a sad graph. What does that tell us about the value of A? I think you might have guessed it. It means that G is minus 9.8. Why negative? Because if it becomes negative, then that would actually explain why we've got a sad graph. The coefficient of the square term, okay, is actually negative, so it means that we'd get a sad graph. Now I want you to please look at this. Okay, so G is minus 9.8 meters per second squared. So if gravitational acceleration is minus or is negative, and we know that downwards, okay, gravitational acceleration is acting downwards, so it means downwards is taken as a negative. So then what does that tell us? It tells us that we must have taken upwards as positive. That is going to be very important in us answering the question, because the examiner might not have told us that, but in this case it will become very important. Okay, right, now I want us to quickly look at the question together. Right, now, so the position of the ball right at the beginning, it starts at 10 meters. So let's check. They say a ball is thrown vertically upwards from a balcony of a building. So it must mean that the balcony must be 10 meters above our point of reference. I assume that the point of reference must be the ground. So therefore, the ball, okay, must be starting 10 meters. If you look at it, you know, the one thing I love about taking upwards as positive for a position time graph is that it kind of gives you a space-time a picture of what is actually happening. Think about it. So it started 10 meters. So if we consider time axis as though it's the ground, so it started 10 meters from the ground, right? And what happened to it? It went up, up, up. It got to a maximum height there, right? And then what happened? Then it started coming down. It passes that balcony again, right? And then it went even further down and lands on the ground. So in a sense, it kind of gives us a picture of what actually happens with the ball. Okay, right. So the first thing that they ask of us is, how high is the balcony above the ground? I think you've already guessed it. Of course, it should be 10 meters, right? So to answer 3.1, we know that the balcony is 10 meters. Okay, above the ground. Above the ground. Sorry for that terrible handwriting there. Okay, I'm trying to squeeze everything in. Okay, right. So it's 10 meters above the ground, right? And then let's go to the next question. 3.2, they say write down the numerical value of time t. Now look at this. What is time t? We know that it took how long? 0.6 seconds to get to the maximum height. You remember that, no? Okay, here it is. To get to maximum height. Now, to come back to the same position, this is what we called our time symmetry, right? So to come back to the same position again, the balcony, it should take the same time, isn't it? So notice there, so it should take 0.6, another 0.6, so 0.6, another 0.6 there. So t, I think you guessed it, t will be 0.6 plus 0.6, and that gives us 1.2 seconds. Okay, right. I hope that kind of makes sense. Okay, let's zoom in there a little bit so that we don't see some ugly stuff there. All right, now then the next part. Okay, so we want to find out, okay, calculate the initial velocity of the ball. Now, the thing about a position time graph is that you are somewhat forced to use position time. Your projectile motion equations. Okay, your 4 equations. Okay, so what do we know there? All right, if we take that as position A, if you don't mind, I'm going to label it. So let's call that position A, let's call that B, let's call that C, and let's call that D. So I'm taking from position A to B, okay? I think that's where I have the most information, right? So from A to B, okay? I want to check, what am I given? I'm looking for initial velocity, right? But what is my final velocity? So means A is my starting point, B is my end point, right? My final velocity when I get to this point, this is my maximum height. I know that my velocity is 0, okay? And then what about my gravitational acceleration? Now please don't forget, we took G as, or rather we took upwards as positive, so G is minus 9.8 meters per second squared. And then what about the time? Okay, how long did it take between the two positions? You guessed it right. We know that it took 0.6 seconds. Okay, and what would be our displacement between those 2 points? We don't know. Okay, because we're not given a value for the maximum height there, so we wouldn't know. Right, so which equation of motion are we can we use? We're looking for initial velocity. I think it's going to be the first one, right? Why am I choosing the first one? Because we don't have displacement. Okay, and we're looking for initial velocity, right? So the only equation without displacement is the first equation, right? So plus g delta t, right? Final velocity is 0. Initial velocity is what we're looking for. Our gravitational acceleration minus 9.8, and the time that it takes, that is going to be 0.6. Okay, we get our calculator out. Okay, all right, so we're going to say negative 9.8 times 0.6. That gives me minus 5.88. So in this case, you've got VI minus 5.88. So if I take this to the other side, it becomes positive. So VI, okay, is equals to 5.88 meters per second. Okay, so meaning that our ball was thrown with an initial velocity of 5.88. Okay, all right, and then let's check there. Okay, and then the next one they say okay, so define the term projectile. We said this is motion under the influence of gravitational force only, right? Or in this case, you can say uninterrupted motion under the influence of gravitational force only, right? And please remember, you must know your definitions, okay? Please don't disappoint me, okay? Right, so then the next question says, calculate the maximum height above the ground, okay, reached by the ball. So remember, we're not just looking for maximum height, we're looking for maximum height above the ground. Okay, so we already have the initial velocity, right? I'm still going to deal with that position between A and B. Which equation? Let's make things easier for ourselves. Okay, doesn't really matter. Can take delta x, okay, is equal to VI delta t plus 1 over 2 g delta t squared. You could have also chosen the second equation, okay. Right, remember I'm doing that for A and B, right? Between A and B, what's my initial velocity? You guessed it, right? Oh, by the way, we got this value to be positive, right? And positive, we know that we took upwards as positive, so that means that it's 5.88 meters upwards. Sorry about that. Okay, right, so this is upwards. All right, so it's a positive 5.88, and the time that it took, remember that's 0.6 plus 1 over 2 times negative 9.8 times 0.6 squared. Okay, right. Okay, we take our calculator again. Let's see. So that's going to be 5.88 times 0.6, okay, plus 0.5 times negative 9.8 times 0.6 squared. Okay, I get 1.764. Okay, 1.764 meters. But remember, they had said we must find that height. Now remember, this 1.764 is the height between A and B. But what did the examiner want? Height above the ground, right? So we want to know how far is it from this point to that point there, okay? We found that height there, okay, to be 1.764. And so what are we going to do? We're simply going to add 10 meters plus the 1.764. So it means that our height, okay, let's bring it up here. So our height is going to be equal to 10 plus 1.764, or you can just, let's round it off to 2. Okay, so that's going to be 10.764 meters. Okay, right. Depending on what the examiner's instruction is, you can round it off to 2 decimal places if necessary. Okay, right. I hope you're still with me. Okay, I hope it still makes sense. So now let's tackle the next part quickly. Right, so now we want to find out, they say calculate the magnitude of the final velocity of the ball when it reaches the ground. Very interesting. Right, now ladies and gents, I want you to listen to me very carefully. Right, so now if you think about it, we don't know how long it took to get to the ground, right? Remember, this time here, t is 1,2, but this is not when it's at the ground. This is when it passes the balcony again, when it comes back, isn't it? So we don't know how long it really took to get to the ground. Do you agree with me, nah? Right, now, how are we going to now find out information about when it lands on the ground? Look, there are several ways. Okay, you can take information from A till D. Now please, I want you to please remember this carefully. All right, so we are going to take information between A to D, and we're going to say, okay, between A to D, let me write it at the bottom here so that everyone can see it. Right, information between A to D. What I'm simply going to do between A and D, what is my initial velocity? Remember, at A, we said our initial velocity was a positive 5.88. Remember that it's going up, right? So 5.88, right? Do we know what the velocity is when it lands on the ground? No, that's what they asked me to find out, right? Gravitational acceleration. Please remember that the value of gravitational acceleration never changes. So in this case, we simply stick to minus 9.8. Why is that? Because remember, we said upwards is taken as positive, right? And so that's 9.8 meters per second squared. And what about the time? We didn't know the time that it took to get to the ground. But what is the displacement? Now, please, ladies and gents, if you noted from my previous videos, right, on vertical projectile motion, I addressed this issue of displacement. We said, what is displacement? It's a straight line change in position from beginning to end point. So if I take my beginning, it's A, my end point is D. So in a straight line, how far is it from A, right, till D? How far is it between those 2 points? Okay, from A. Now, remember, when it went up 1.76, it also went down another 1.76. So it means that your displacement between A and C is 0, right? So as a result, from A to D, it's actually going to be 10 meters, but it's 10 meters downwards. So please note, we said up is positive, so therefore down should be negative. So that's going to be minus 10. I know that is where a lot of people tend to lose it, in a sense that they would forget to put this negative, because remember, it is now being displaced downwards from A till D, which is on the ground, right? Where was it going? It's going down. It's displaced downwards. And we said up is positive, so therefore it means down should be negative. Okay, right. So we're looking for final velocity. We don't have time. Okay, so Vf squared is equals to Vi squared plus 2 times G delta x. Okay, final velocity, that's what we're looking for. Initial, that's positive 5.88 squared plus 2 times A, that's minus 9.8 times delta x, which is minus 10. You notice if you didn't put that negative there, that would make that whole term to be negative, right? So we've got 5.88. Okay, our calculator. Once again, 5.88 squared plus 2 times, it's a negative 9.8, and times negative 10. Okay, right, so we get that value there, but remember, Vf squared is equal to that, but we are looking for Vf, right? So it means we're going to take the square root of the answer. So I get a value of 15.18. Now, ladies and gents, very importantly, the examiner said we should look for the magnitude of the final velocity. But if the examiner had said we should find the final velocity, which means we would have had to also determine the direction as well, right? Now, I want you to think about it. Where was it going when it landed on the ground? It was going down, isn't it? Right? We said up is positive, so down should be negative. So in this case, remember, when you're taking a square root, you always end up with two possibilities, plus or minus, right? So when you're tackling questions, you must always be mindful of this. So which answer are we going to pick? We should pick one. So on the ground, sorry, it was actually moving at minus 15.18. And why a negative? Because in this case it was going down. We've taken up as positive. But nonetheless, this doesn't matter for this question, because the examiner clearly had said we must actually just work out the magnitude of the velocity, right? Okay, and we get to the conclusion of the question. They say draw a velocity versus time graph for the motion of the ball. Indicate the following on your graph: initial velocity, final velocity, the time taken to reach maximum height. Now, remember, okay, so velocity, because it is a vector quantity, you must have both positive and a negative side. So we know this is going to be time and this is going to be velocity. Okay, let's say velocity, and that is in meters per second. Please don't forget to label your axes, right? Now, remember, velocity time is a straight line graph, right? So what was the initial velocity? At time 0, what was our initial velocity? It was positive 5. You're quite right. 5.88 rather, right? So this value here, so will be 5.88. It's that value here, the positive 5.88. But what happened? As the ball went up, the velocity was decreasing until it got to 0. So in this case, Started at 5.88, decreased until it got to 0. Decreased in the positive direction. It's going up, isn't it? Right? And then what happened? Right, then it started going down. So it was positive all along, it got to 0. Positive all along, it got to 0. Okay, and then the velocity now starts increasing, but in the negative direction. So in this case, you're going to have a graph that looks something like that. Okay, so now remember, we said this value here is 5.88. Okay, this is when it actually crossed the maximum height. Okay, this is 0.6. Okay, this is this point there. Okay, and what else do we know? We also know the final velocity. Okay, we know when it landed on the ground. Okay, let me just stretch that a little bit. Sorry. So I know when it landed on the ground. It's at 15. We said, and by the way, you see where that issue of having a minus 15.18 comes in, right? So this is minus 15.18 meters per second, right? So left there at 5.88, landed on the ground at minus 15.88. We didn't calculate the time that it took to land on the ground, but if we had that time, we'd insert it there. But if you don't have it, please don't even bother trying to get that value. Okay, right. Just one thing I want to kind of talk about, because I haven't really spoken about the acceleration time graph. Now, if you think about it, ladies and gents, if I was ever asked to draw a acceleration time graph, remember, acceleration is a constant 9.8 throughout the motion of the ball, isn't it? Right? So if you think about it, if I were asked to draw an acceleration time graph, okay, so this would be acceleration, okay, in meters per second squared, right? So what would our graph look like? Remember, in this particular case, we took upwards as positive, so as a result, it means that acceleration is minus 9.88. So your acceleration graph would be, okay, a negative graph there. It's constant. Can you see? So this value is minus 9.8. Okay, so this is how simple your acceleration time graph would look like. Okay, right. I really do hope that this was very helpful. I know it's all mixed up and you've got all values all over the place there. Okay, right, but I hope that it makes sense. And then now we're going to tackle the very last question. I also wanted to base it on a position time graph. Okay, so let's go into it. All right, so we tackle our very last question. Okay, I'm sure you should be screaming at the top of your lungs. Yippee! Okay, so the very last question, I'm taking this from the November 2020 question paper. Quite a number of people had complained, about how difficult this paper was, but you'll see that some of the questions, if we really kind of understood our content, we would have tackled it quite nicely, right? Now, again, we're given a position time graph. Can you see that? I'm glad you can already see that it is a sad parabola. Okay, so what does that already tell us? It tells us, yes, you guessed it right, that they must have taken upwards as positive. So at least once you have that settled, then it will be easier for us now to tackle the question, right? Okay, they say a small ball is dropped from a height of 2 meters and bounces a few times after landing on a cement floor. Ignore friction, right? They say the position time graph below, not drawn to scale, represents the motion of the ball. All right, so let's look at the motion of the ball. So it started 2 meters from where it was dropped. Okay, remember they said to us it is dropped, so that's very important. Okay, what does that already tell us? It tells us that we must the initial velocity rather was 0. Okay, right. Right, because we know obviously the point from where it was dropped from is also a stationary point, right? Okay, and then they told us it bounces a few times. So what happened? This ball must have been dropped from a height of 2 meters. Whee! It went down. Okay, so this represents a delay on the ground. You remember with our first question, right? There was a little bit of a delay, so it means when it landed on the ground, it landed at a time of 0.64, and it left the ground after at 0.67 seconds. So it means the time that it spent on the ground would be the difference between that. Okay, and then there's another time that it spent on the ground again. So by the way, this shows us that by the way, you'll notice that every time that after it bounces, it never gets back to the same maximum height. So this simply tells us that obviously it keeps losing energy. So it's an inelastic collision. But nonetheless, okay, let's tackle the question. Right. So they say define the term free fall. Okay, remember we said that this is uninterrupted motion under the influence of gravitational force only, right? You can define it in the way that you want, but the main salient points in that case would be that it is moving under the influence of gravitational force only as the only influence on it. Okay, right. Now they say use the graph to determine. Okay, right, I'm gonna just take it up a little bit. Okay, so use the graph to determine, okay, the time that the ball is in contact with the floor before the first bounce. Okay, remember the bounce is when it goes up. Okay, so the time that it is in contact with the floor. So I think you got that. So 3.2. So the time that it is in contact with the floor would be 0.67 minus 0.64. So 0.67 minus 0.64. Okay, so that gives us 0.03 seconds. Okay, right, so it must have spent 0.03 seconds on the ground. Okay, and then second question, the time it takes the ball to reach its maximum height, okay, after the first bounce. All right, so now the time it takes to reach the maximum height after the first bounce. So here's our first bounce. Okay, there is the maximum height. So it fell, spent some time on the ground, went to maximum height, came back again on the ground. Now, if you notice, it went up and then came back down. So how long did it take for it to go to maximum height and come back down? Okay, so we will say, okay, that will be 1.9 minus 0.67. Okay, so that gives us what? It gives us 1.23. So remember, that's the time it takes going up as well as coming down. Notice we've got a time symmetry here. Okay, so it means that the time it takes going up should be the same as the time it takes coming down, isn't it? So now we are just looking for that time there. Okay, how long did it take to get to maximum height? So we're going to just divide that by 2. Okay, so that's 0.615 seconds, okay, to get to maximum height after the first bounce. So that's 3.2.2. So how long did it take? It took a time of 0.615 seconds. Okay, now I want you to again be very careful. There's a different way of looking at this question. Now someone might say, yeah, but initially in that question you said you must actually add that time there. But remember, they're not looking for the time on the graph. They're not looking for this time. Let's say if they had marked this as T0. Okay, I see we've got a T there. If they had marked it as T0, let's say, then if they were looking for T0, then I would have said, okay, it's 0.67 and add to that 0.615, okay, plus 0.67. So that time there would be 1.285, okay? But this is in reference from the point when it left, when it was dropped, okay? It would have taken 1.285 seconds to get to that point. But nonetheless, in this particular case, they just wanted to know how long it took from the moment it left the ground after the first bounce. That's what they said, right? Until it got to the maximum height. Okay, I hope you can you can understand, you can follow the logic of what I'm trying to show you there. Right, and then the next one, they say calculate, determine the speed at which the ball leaves the floor at the first bounce. So we want to know, at what speed did it leave the floor? Okay, now I'm going to do what I did before. If you don't mind, let's say this is point, okay, let's take a different color pen. So let's say this is point A. This is B when it landed. This is C when it left the ground. This is D when it left, when it got to maximum height. This is E when it landed again on the ground. And then this is F when it left the ground, bounced for the second time. G and H, right? Okay, so they want to find out the speed at which the ball leaves the ground, leaves the floor rather, at the first bounce. So this is the first bounce. We want to know this velocity here. Now, help me out. So it means I'm looking at different ways of tackling it. So we can take from C to D, right? So let's say if we took, okay, if you don't mind, can I just write it over the side here? Okay, over the side here, it's easier for me. So I'm going to take information between C to D, right? Okay, so initial velocity, we don't know what it is there. Okay, we don't know at what speed it left. Final velocity, remember maximum height. What happens at maximum height? You're quite right, it stops. Okay, gravitational acceleration. I hope you remember what we had said earlier. We took upwards as positive, that's why we've got a set graph, and as a result that's minus 9.8 meters per second squared. How long did it take? Now you remember we just found the time. Okay, we said it took 0.615 seconds. So that's 0.615 seconds. And then what about the displacement? Okay, so we find out from there till there, okay, from position C to D, it's 1.8 meters upwards. So it must be positive 1.8 meters. Remember, we took up as positive, right? Okay, so we're looking for initial velocity. Okay, I'm just not going to waste my time. I'm going to use the first equation. You know, anytime you can use the first equation, always try to do that. It's VI plus G delta T, right? So my final velocity, that's 0. Initial velocity, that's what we're looking for. G, That's minus 9.8. And what about the time there? That's 0.615. Sorry about that. I'm going to squeeze it in there. All right. So let's calculate quickly. Okay, so we're going to say negative 9.8 times 0.615, and we get 6.027. Okay, so VI minus 6.027. Okay, and then if I take that to the other side, it becomes positive, so it's going to be 6.027 meters per second. Okay, obviously in this case they said to me the speed, so I didn't need to show the direction, but if they had said calculate the velocity, then I would have had to show the direction. We got a positive value, and we know that upwards is positive, and obviously at point C it was actually going up. Okay, right, I hope you get the point. All right, and then the very last question. Usually I've seen that people get scared when they see something like 6 marks. Okay, all you need to do, please calm down and just make sure that you just follow the right principles. Okay, right, I want us to tackle this together. Right, so we're looking for time t there. Okay, now there are several ways in which we can look at this question, right? So we can look at it from a perspective of finding out the time between F and G. But here's my issue. Between F and G, I do not have the initial velocity when it left the ground there. Do you agree with me? Right? So instead of that, rather let me work between G and H. Okay? Right. Right, let's see what we have between G and H. Okay, so let's take information between G to H. Okay, so initial velocity, do I have that there? Okay, remember this is at maximum height. What do we know about maximum height? That the velocity is 0. So I'm taking that as my starting point, right? So it started with a velocity of 0 at G. H is my final point. So final velocity at H, we don't know, but we know what gravitational acceleration is, right? We said that's minus 9.8. And then do we know the time that it takes? No, we don't. Okay. Do we know the displacement? Okay. Displacement between G and H. Notice they said it started at 1.2, right? And it got to 0. So it was displaced 1.2 meters downwards. Okay. So it was displaced 1.2 meters downwards. Remember we said up is positive, so yes, you guessed it. So this must be negative 1.2 meters. Remember, because I'm considering G to H, okay? Remember, it would be going down at that point. So going down, that should be negative. And remember, going up or being displaced upwards would have been positive. Okay, right. Now, okay, we're looking for time. Okay. Which equation of motion? Okay, one without final velocity. So we'd say, we're going to say delta x is equal to VI times time plus 1 over 2 a delta t squared. Okay, right, let's substitute. So we've got minus 1.2, which is equal to initial velocity, okay, we said it's 0, Okay, so that it makes that whole thing 0, plus 1 over 2 times minus 9.8 times delta t squared. Now, something that we must do there. Okay, so this is minus 1.2. Half of 9.8 is minus 4.9. Okay, delta t squared. Okay, so it means both sides I must divide by minus 4.9. Okay, minus 4.9. That cancels with that, so that I'm left with just the t squared there. So that's negative 1.2 divided by another negative 4.9. Okay, or you could have just realized 1.2 over 4.9. The negatives actually can just, if you divide by negative, gives you a positive, right? Okay, so this is the answer that I get. Okay, but remember this is delta t squared, so it means that I must take the square root of that answer, and I get that delta t is 0.495. Okay, yeah, let's just say 0.495 seconds. Okay, right, ladies and gentlemen, now it comes back to what we were saying earlier on. They are looking for t, a point on the graph. They are not looking for the time lapse or the passage of time when the ball left the maximum height until it reached this point, right? So what I do know is that, now please, I want you to remember, it took the same time going up, okay, getting to that point there, up until maximum height, okay, and it took the very same time from that point there to get to that here. Now, how long did it take to reach point G? So it must have been 0.495. So it means, what would be the time there? It's going to be 1.97, okay, 1.97 plus 0.495. 0.495. Okay, right, that's the time there. And what's that time? It would be 2.465. That's the time there, right, at this point here. Okay, right, but now we're not looking for that time there, we're looking for that time there. So what do? We add another 0.495. So plus 0.495. Okay, and what do we get? 2.96. So we find that time t is equal to 2.96 seconds. Okay, great stuff. Now, of course, there is another way that you could have tackled that. Let me just show you quickly. Okay, you could have actually found out what the initial velocity is there. You know what the final velocity is. Okay, you know the displacement, you know gravitational acceleration. You could find out the initial velocity and then work between G and H, right? Find the time between G and H. You would know what the initial velocity is, you would know what the final velocity is, right? Because it would be the same as that initial velocity except for the sign. Okay, find the time between those 2 points, sorry, F and H, I said G and H, F and H, and then add that to the 1.97. You should be able to get the same time. Obviously, look, this was a very interesting question, but I hope that your knowledge on graphs is a little better now. And obviously I've tried to, tackle quite a variety of questions. But once again, ladies and gents, if you have any more questions on graphs, or you've got graph questions that you'd like for me to tackle, you're more than welcome to hit me up on my email or even comment below. All right. And my email address is mlungisi, that's MLUNGISI .m.ngosi, my surname, NKOSI, @gmail.com. Until we see each other again, thank you, thank you, thank you, thank you, and keep shining. Science is fun. Sharp, sharp.